Okay, picking up the second portion of our review of simple harmonic motion, we've taken a look at a spring mass object vibrating back and forth besides a equilibrium position. We talked about the equation associated with that wave if you were to graph it position with respect to time. And now we need to talk a little bit about this other portion of this other type of simple harmonic motion, or the periodic motion associated with a pendulum. In this case right here, you can kind of see the pendulum has just been drawn off a certain distance away from an equilibrium point. And so our equilibrium point now is kind of the bottom of the fall of our pendulum. And whenever you draw this pendulum here, the point that I just made there, the bottom of the fall, is extremely important, because every time you draw one of these, you should be visualizing this sort of an arrangement here, where in this case right here you have some kind of change in height, between the initial position and the final position of your pendulum. And that is, of course, where it's getting its energy. It's trading back and forth gravitational potential energy associated with its fall. We can answer questions about the motion, not using motion diagram or motion equations again, because the acceleration in this case is continually changing. The acceleration, of course, is not g in this case, because g is not it's not in free fall. But we can use energy to take a look at pendulum problems, and it's going to be kind of a similar setup. We're going to have, let's say, an initial kinetic energy, initial gravitational potential, initial spring, if there are any springs involved, plus or minus some work, would equal the final values for each of these energy components, something like this. And this is going to simplify, because with no springs and no friction involved, you're going to see that this system is going to trade. Let's say we'll use our initial situation as when the ball has been pulled away. It's going to have gravitational potential energy because it's been pulled upward. Not the sideward motion, but the vertical height motion only is what we care about. And let's say if we use the bottom of the swing here, we could use some intermediate point, but in this case I'll use the bottom of the swing. That potential energy, gravitational potential, has been converted into some kind of a kinetic energy, and we have some kind of a term that looks like this. These are well known and have been reviewed elsewhere. This is going to be some kind of an mg change in height, or mgh sort of thing. Or initial height, depending on where you put your 0 point for your height. And this, of course, will be a 1/2 mv squared sort of a thing. Let's say for this second position here, whatever second position you want to measure. And that's how you analyze this with energy. Now, there's a basic equation here associated with the time. Once again, we have a period here, a new equation for the period of a pendulum, and it's equal to 2 pi times our square root of the length divided by g. So our length of our pendulum, something like this, is what's of interest. And you can kind of see here in this case that as the pendulum gets longer, its period increases. And g you can think of as near Earth's surface as a constant, of course, but you could go to another planet, or you go to the moon, where if this quantity is smaller, I'd be dividing by a smaller number. The period then gets larger, and that should make sense. So on the moon, for instance, this would be a slower, in other words, a longer period of time between each cycle, kind of a slower swinging of the pendulum, something like that. Notice the important thing here is mass is not part of this. So you'll see in these problems, they may give you the mass, for instance, of the pendulum, but it's irrelevant. And this is, you can kind of think this as being related to the fact that you can take two different masses, drop them, and they drop at the same value for g. It's kind of related to that sort of a thing. It's independent. The period depends on g, but it doesn't depend on the mass of the object. And that's our kind of basic relationships. I should box that because that's one of the equations on the equation sheet as well. Now, let's see, one more thing to cover here with these pendulum problems in particular is you'll notice that the pendulum problems there are some geometries associated with these problems that do bring in some trig. So for example, there's an angle here that this can be pulled away from the vertical, and you can kind of see here some triangles happening there. And so there are some possibilities with these problems that you'll have to break the kind of break this into certain triangles and use that angle to solve your problems. Also notice that this length here can also be considered a radius, because this is like a portion of a circle. So if we were to, if we were to continue this around, this in fact is a subset, right? This is a subset of circular motion. So it's really kind of a circular motion problem, and in part a simple harmonic motion problem as well. What this means, of course, is that let's say we want to analyze the situation of the object, let's say when it's at the bottom of the swing right here. When it's at the bottom of the swing, it has some kind of, let's say, velocity that's tangent to the path going in this direction. And if we wanted to analyze this, we would say, well, it would have a tension acting up, some kind of a tension force. I guess I should do force of tension so that I don't get this confused with period here. That probably looks a little bit better, force of tension. And then I also have a force, an mg, acting down. It should make sense that the tension force has to be greater than mg so that I have a net force pointing up, which points out that these pendulum problems are also circular motion problems where you can be asked to do the sum of the forces at any point. At the bottom here, you'd have some kind of force of tension minus your mg is equal to some kind of an mv squared over r sort of a relationship. And that would allow you to solve for certain parameters for pendulum problems. One last kind of finer detail, I'm going to kind of zoom in on my picture of what's happening with our pendulum here, and notice that at the bottom of its path here, you can kind of see here that there are no horizontal forces acting on the pendulum weight, the mass. So in this case right here, you can kind of see this is the place where the acceleration in the left-right direction is at a minimum. And if I were to take a look over at the position when the ball is over here, you can kind of see that my force of tension now is going to be acting in this direction. It is going to have some kind of a component this way. In other words, some kind of an F in the X direction, and it's going to have some kind of a component in this direction. In other words, a Y component of the tension. And you're going to still have the mg acting down, something like this. And you can kind of see as this pendulum is pulled further and further away from the equilibrium position, this X component of the tension force gets greater and greater, and that of course provides the acceleration for the object. So the horizontal acceleration of this thing speeding up is given by that component, and then you have of course the vertical component maybe balancing the g. What this means is you have a little bit more complicated picture as far as the acceleration of the object when you're looking at a pendulum than you did in the object when you had a mass with a spring. And in this case right here, you have some kind of an acceleration vector. You have some kind of an acceleration vector that'll be somewhat towards the center, providing centripetal acceleration, but also somewhat of a tangential component of acceleration, allowing the bob to speed up. Remember that because that acceleration is always changing, because the forces are always changing, that's what does not allow us to use motion equations to solve for things associated with this. And that gives us our complete review now for simple harmonic motion. Thanks for joining me.